Cultivating phytoplankton is all about creating the right conditions. Like plants on land, they need four essentials: light, nutrients, carbon dioxide, and stable temperature control. There are two main systems used to produce phytoplankton. The first is the open pond system, also known as raceways. These are large, shallow outdoor ponds, mixed continuously by paddle wheels. Open ponds have some clear advantages. They are less expensive to build and operate. And their design is simple and easy to manage. But there are also limitations. Productivity per unit area is low. They are easily contaminated by other algae, bacteria, or predators. They depend heavily on weather conditions. And they lose a significant amount of water through evaporation. The second major system for phytoplankton production is the photobioreactor, or PBR. These are closed, transparent systems, built from glass or plastic tubes, flat panels, or even flexible bags. Photobioreactors offer several advantages. They allow for precise control of pH, temperature, and light. They achieve much higher productivity and biomass concentration compared to open ponds. Because they are closed, the risk of contamination is minimal. And they lose far less water through evaporation. But these benefits come with trade-offs. The initial capital cost is much higher. Operation and maintenance are more complex. And under certain conditions, photobioreactors can suffer from overheating and oxygen buildup. Phytoplankton, like plants on land, need the right conditions to grow. Two of the most important requirements are light and nutrients. Light is one of the most important requirements for phytoplankton growth, but it can also become a limiting factor. In pond systems, light penetration is often reduced by self-shading. As the culture becomes denser, cells block light from reaching deeper layers. Because ponds are outdoors, growth also depends heavily on weather and natural sunlight. In contrast, photobioreactors are designed to optimize light exposure. Their closed structure and high surface-to-volume ratio allow more even distribution of light. This design reduces shading, improves efficiency, and supports higher productivity. Phytoplankton require nutrients such as nitrogen, phosphorus, potassium, and trace metals. But how these nutrients are managed differs greatly between ponds and photobioreactors. In pond systems, nutrients are added directly into the water. However, a significant portion is lost to the surrounding environment. Some are consumed by contaminating organisms, reducing efficiency and lowering yields. In photobioreactors, nutrients are supplied in a sterile and highly controlled manner. Dosing is optimized to match the needs of the culture. This results in minimal nutrient loss, greater efficiency, and much higher productivity. Carbon dioxide, or CO2, is another critical requirement for phytoplankton growth. It provides the carbon that cells use during photosynthesis to build proteins, lipids, and other essential compounds. In pond systems, CO2 is bubbled into the water. But this method is highly inefficient, with as much as 80 to 90% escaping back into the atmosphere. In photobioreactors, CO2 is injected into a closed-loop system. This design ensures much higher efficiency, with over 70% of the gas taken up by the culture. The result is better growth, reduced waste, and more sustainable use of resources. Once phytoplankton have reached sufficient density, the next step is harvesting. This happens in two stages. The first is bulk harvesting. One common method is flocculation, where chemicals such as chitosan, or even a simple pH adjustment, cause the algal cells to clump together and settle. This method is low energy and cost-effective, making it an excellent first step. Another option is flotation, where fine air bubbles are introduced, lifting the cells to the surface where they can be skimmed off. This works especially well for certain species. The second stage is thickening. Here, the goal is to concentrate the algae into a slurry containing about 15 to 25% solids. The industry standard is centrifugation. A high-speed disc stack centrifuge spins the cells out of the water with great efficiency. However, this method is energy-intensive and represents a significant operational cost. Once harvested, the biomass moves to processing, where it must be stabilized into a usable form. This usually means drying. The most common technique is spray drying, where the slurry is sprayed into a hot chamber, instantly turning it into a fine powder. For premium applications, freeze drying may be used. In this process, frozen paste has its water removed through sublimation, producing the highest quality powder with excellent nutrient preservation, but at a much higher cost. The end result is a dry, shelf-stable powder, carefully tested for quality and then packaged, ready to be used as feed in aquaculture systems. As for conclusion for this topic, the choice between photobioreactors and open ponds is always a trade-off between cost and control. Open ponds are the most cost-effective option. They are well suited for large volume applications where some contamination can be tolerated, such as in the production of biofuels. On the other hand, photobioreactors are essential when the goal is precision. They provide high control and purity, making them the system of choice for high-value products like pharmaceuticals and advanced nutraceuticals. No matter which system is used, harvesting remains a major challenge. Centrifugation is still the most reliable method, but it is also highly energy-intensive, making it one of the biggest costs in the entire production chain.